Hello, everyone. I'm Surud More from the Inter-University Center for Astronomy and Astrophysics in India. On behalf of the Weak Lensing Working Group of the Subaru Hyper Suprime-Cam collaboration, I welcome you all to this webinar. We are quite excited today to announce the cosmology results from the analysis of the HSC Year 3 data. The Hyper Suprime-Cam survey is a Subaru strategic program run by an international collaboration between astronomers from Japan, Taiwan, and Princeton University. The survey is possible due to generous support from a number of our funding agencies. We are also thankful to a number of institutes such as Princeton University, NAOJ, Kavli IPMU, and KEK for support in instrumentation and software development. Importantly, we also acknowledge that observations on which our analyses are based were carried out at Mauna Kea in Hawaii, and we are grateful for the opportunity to observe the universe from such an important place, which has both cultural as well as historical significance. So let me start by giving you a picture of the rogues gallery of people who have been involved with the weak lensing work in HSC, the results of which you will hear today. In particular, I would like to highlight the earlier career scientists here at the top who contributed significantly to the analysis. You will hear from them today in the webinar. We, of course, span multiple continents, which means that we have to often work at odd hours. So I have to acknowledge the efforts and the sacrifices required by the entire team, as well as their family members, to make this collaboration successful. Here is a list of papers that describe the key results. Some of them you may have already seen on the archive earlier, along with 5 new ones which will appear today. All these papers are available right now for you to take a look at if you go to the URL, which is mentioned at the bottom of the slide, or you could scan the QR code in the corner. Finally, here is the structure of today's webinar. We will have 7 short presentations that will last about 45 minutes. 5 of these talks come from early career scientists, and these are sandwiched between the overview talk, which will be given by my colleague Hironao Miyatake, and the summary of the results at the end by me. This will then be followed by a question, answer, and discussion session, which will be moderated by Rachel Mandelbaum. So please drop your questions within the webinar Q&A feature. You can ask these questions anonymously in case you want. You could also take a look at the questions which have been asked by other people and upvote the questions which are asked before. Unfortunately, we will not be able to monitor the raised hands. And so we just encourage you to use the webinar Q&A feature. With that, I will pass on the spotlight to Hironao Miyatake for the overview talk. Hironao.
Thank you. Hello, everyone. I'm Hironao Miyatake from Kobayashi Masukawa Institute at Nagoya University. I'll give you a brief overview of the HSC survey and our cosmology analysis. In the recent few years, the standard cosmological model, the so-called lambda CDM, has been challenged by precision measurements of large-scale structure, or LSS. The cosmological parameter, S8, which is a combination of sigma 8, the clumpiness of the cosmic structure, and omega m, energy density of matter component, including dark matter, has been measured by early universe probe, CMB, and the late universe probe, LSS, such as weak lensing, galaxy clustering, and the galaxy clusters. And it has been pointed out that LSS measurements prefer the smaller S8 compared to CMB if we assume lambda CDM is correct. This is called the S8 tension, and now it is a time to perform stringent tests of lambda CDM to check if S8 tension is true. So it is not straightforward to extract cosmological information from LSS because most of the matter in LSS is dark matter, which does not emit light. Thus, we cannot measure LSS by looking at the galaxy. Here, weak lensing a subtle and coherent distortion of galaxies caused by LSS between an observer and distant galaxies is a powerful proof of LSS because it enables us to measure the matter distribution without distinction between ordinary matter and dark matter. The traditional weak lensing cosmology probe is called the cosmic shear, which is the autocorrelation of weak lensing shear. The other probe, the so-called 2x2 point, turned out to be another powerful LSS probe and became the standard cosmological observable in the past decade. The 2x2 point is a combination of galaxy-galaxy clustering and galaxy-galaxy lensing. When we combine cosmic shear and 2x2 point, it is called a 3x2 point. Hyper Suprime-Cam is a prime focus camera of Subaru telescope. It has 1.5-degree diameter field of view, huge light collecting power, and a superb image quality, like seeing is routinely around 0.6 arcsecond. These features make HSC one of the best weak lensing machines in the world. Using HSC, we conducted Subaru Strategic Program Survey. The survey consists of 3 layers: wide, deep, and ultra deep. Among them, the wide layer is designed for weak lensing cosmology, which covers about 1100 square degrees by GRIZ and Y bands with a limiting magnitude of 26. So it's wide but quite deep. The HSC survey overlaps with other major surveys such as BOSS and ACT. Actually, in our analysis, we use both spectral samples, as we explain later. The survey started in 2014 and was completed in 2021. But in this webinar, we will give results from the data taken up to April 2019, which covers for 16 square degrees of the sky. This diagram shows how our analysis were designed. From the data, we have to first produce intermediate data products, such as shape catalog and photosy, and then we perform these measurements, and finally do 4 cosmological analyses: Fourier space cosmic shear, real space cosmic shear, large scale 3x2 point, and small scale 3x2 point. Note that the references highlighted by red are the 5 papers we got out today. And those surrounded by red squares will be explained in detail in the following presentations. We conducted blind analysis to avoid confirmation bias. This figure actually summarizes what we did. We did the catalog level blinding. We prepare 3 blinded catalogs with a slight offset of weak lensing shear calibration, and one of them is a true catalog. The analysis of each blind catalog is shown in this figure, and you can see a slight shift in S8. And we did not know which one is true. We designed the blind catalogs so that the difference between blind 0 and blind 2 becomes about 0.1 in S8, which is larger than the S8 difference between CMB and LSS. So we cannot guess if our S8 constraint is close to Planck or not. We also did the analysis level blinding. When plotting a contour, we blind the center value. For example, in this figure, the figure is shifted by the mode of blind 1 analysis. So we see the center is at 0. We do systematic test while blinding, which is stress tests with various analysis choices. After systematic tests passed, we finally unblind the result. Okay, so let me jump into the summary of our result. Our 4 analyses are consistent with each other and exhibit consistently smaller S8 compared to Planck. Details of each analysis will be explained in the following presentations by our junior members. So next presentation is about the HSC Year 3 shear catalog given by Xiangcheng Li.
Thank you, Hirona. So I'm Xiangcheng Li. I'm a postdoc at CMU, and I'm going to briefly introduce the HSC Year 3 shape catalog that is used for the cosmology constraint. So this slide is it's the overview of the HSC 3-year shape catalog. So we measure the shear from 25 million galaxies selected from the HSC image, and the figure on the lower left shows the galaxy number density and the survey area. And we compare those with the other stage 3 weak cleansing surveys, and we know that we have the largest effective number density, and we're the deepest one among the 3 because thanks to the good seeing condition of the Hyper Suprime-Cam. And the figure on the lower right shows the number density distribution across 6 different subfields of the HSC Year 3 weak cleansing survey footprint. And okay, one important aspect of the shear catalog production is to test and calibrate the shape estimation bias using realistic image simulation. So we start the simulate galaxy image with a non-input shear, and we measure the shear from the image simulation, and we quantify the biases in the shear estimation. So for the figure on the upper left, it shows how we make the image simulation. We downgrade the high resolution image from the Hubble Space Telescope to the HSC noise level and seeing size. And the figure in the lower left shows the comparison between the simulation and the real data of the 2D galaxy number distribution over the different galaxy properties. For example, the galaxy resolution, signal to noise ratio, and magnitude B. So as shown, our simulation matched well to the real data within 1%. So we believe we have a good systematic error control for the shape measurement. And another really important aspect is to modeling is to quantify the PSF systematics error in the shear estimation. So in the survey, we use the star image to model and interpolate the point spread function at the position of the galaxy, and we remove the influence of the PSF from the shape measurement. So during the PSF modeling, we reserve 20% of the stars that is used to test and quantify the PSF PSF modeling error. And in the figure on the right, it shows the correlation of the PSF modeling error and the PSF shape. So, and the gray region shows our requirement. And so we find that the PSF systematics is comparable to our requirements. So we need to like quantify and marginalize over this PSF systematics in our weak cleansing analysis. And this slide shows how we quantify the influence of the PSF systematics in our galaxy shape measurement. So we cross correlate the galaxy shape with the star shape and the shape measurement error. So any non-zero correlation indicate the PSF systematics remnant in the galaxy shape measurement. And after that, we measure and marginalize this over during our cosmology constraint. And the figure on the right shows the difference, the systematics bias caused by the PSF systematics to our cosmology constraint. The bias is about 0.3%, but we carefully model and marginalize this over it. So this is the end of me. So next we will hear Tianqing talk about the source redshift distribution inference.
Thank you, Shangcheng. Hi, everybody. I'm Tianqing Zhang. I'm a grad student at Carnegie Mellon. Today, I will introduce the redshift-related work surrounding the HSC Year 3 cosmology results. The redshift of HSC Year 3 galaxies are estimated by its photometry in its 5 wide bands, which we'll then call the photo-Z. Here are the photo-Z related work surrounding HSC Year 3 cosmology. In HSC Year 3, we have 3 independent redshift estimation methods for individual galaxies. We have template fitting code called Mizuki, and 2 empirical methods, DMPZ and DNNZ. The photo-Z are calibrated by external spectroscopic and multi-band dataset, and these are described in Nishizawa et al. Secondly, the inference of redshift distribution, which goes into the modeling of cosmic shear and 3x2 point analysis, is described in Raw et al. Lastly, the modeling choice of marginalizing photo-Z uncertainty is described in Zhang et al. For cosmic shear analysis, the HSC Year 3 source galaxies are subdivided into 4 tomographic bins from z equal to 0.3 to 1.5. We remove galaxies with 2 peaks on their redshift probability density function, or PDF. The example on the right shows that our cut can remove the peak around z equal to 3 for our bin 1 redshift distribution. The redshift distribution are inferred by combining 3 parts of information. First, the photo-Z PDF. Second, the cosmic variance, and the cross-correlation with Chimera LRG, which is a red sequence technique that finds the luminous red galaxies in our footprint. In this plot, we showed the redshift distribution for 4 bins in our cosmic shear analysis. The gray area is the DNNZ photo-Z likelihood, with uncertainty computed by cosmic variance of the calibration data. The black bars represent the cross-correlation between the HSC source and the Chimera LRG. The red area represents the combination between the photo-Z and the cross-correlation. Notice that because the Chimera LRG is limited by z equal to 1.2, the source galaxy above z equal to 1.2 is not calibrated by Chimera LRG. Modeling and marginalizing the redshift distribution uncertainty is important for reporting unbiased cosmological results for weak lensing analysis, especially for S8. We choose to use the mean shift model, which shifts the entire photo-Z distribution on the redshift without changing its shape. In each redshift bin, we assign 1 parameter to allow the distribution to shift. We validate the mean shift model using a variety of mock tests. Here we will show 2 of them. Firstly, we performed a mock cosmological analysis with the mean shift model and a more sophisticated model called Bayesian resampling. We find no significant shift or change in contour in the omega m S8 plan. This is shown on the right. In addition, we test statistical coverage in the omega m and SA plan to make sure that our mean shift model has good coverage over the SA range of our concern. And our conclusion is that the mean shift model is suitable for HSC Year 3 cosmology analysis. Lastly, I want to emphasize how we determine the prior of the mean shift parameters. So for the first and the second bin, we choose a Gaussian prior that combined uncertainty of DNNZ and DMPZ and the difference between the 2 methods. For the third and the fourth bin, as we will later find out, we find a potential inconsistency between the informative prior provided by the redshift distribution inference, which sits around 0, and the posterior of Z3 and Z4 if we set the prior to a flat distribution between -1 and 1. We suspect that this problem originates from the inability to distinguish high redshift galaxies in our photo-Z estimation, and the inability to calibrate that using Chimera. To confirm this inconsistency, we conduct a mock test. Given a flat prior, the mock analysis have no photo-Z mean shift, but our real data vector shows a significant shift from 0, which is not a statistical anomaly. To make a conservative choice and avoid bias in our cosmological parameters, we adopt the flat prior as our fiducial choice for the third and fourth spin in the cosmic shear analysis, and the single redshift parameter for the 3x2 point analysis. So that will be it from me. And next, we'll hear from Ruhi Dalal about cosmic shear analysis using power spectra.
Thank you, Tianqing. My name is Ruhi Dalal, and I'm a graduate student at Princeton University. I'll be giving you an overview of our cosmic shear cosmology analyses, and I'll be focusing specifically on the analysis that I led, which uses cosmic shear power spectra. So in general, when we are constructing cosmic shear data vectors, there are a number of different methods or summary statistics that we can use. Two of these that I'll focus on are the 2-point correlation function, which measures the correlation of shapes of galaxies with an angular separation of theta, and the angular power spectrum, which measures the second moment of the Fourier transform of the shear field. And this is a function of angular multiple, or L. In HSC, we believe it's important to carry out our cosmology analysis using both sets of summary statistics, because these are complementary to each other. Not only are the two statistics sensitive to different scales, they also have different treatments of observational effects, as well as different sensitivities to systematics. So it becomes an important and strong internal consistency test to make sure we are able to get consistent constraints from the two approaches when using unified analysis choices. I've shown on the bottom here two examples of our measurements of these summary statistics for the highest redshift bin used in our analysis. The 2-point correlation functions are on the left, and the power spectrum is on the right. One thing to keep in mind as we look at these plots is that for 2-point correlation functions, larger angular separations correspond to larger scales, so larger scales are to the right of these plots. On the other hand, for angular power spectra, smaller angular multiples correspond to larger scales, so larger scales go to the left of this plot. So in order to actually measure our cosmic shear power spectra, we need to account for the fact that HSC consists of 6 different fields on the sky, which leads to a complicated survey geometry. Taking a naive Fourier transform of our shear field would be a biased estimator of the power spectrum because of this partial sky coverage. So we correct for this bias using a technique called pseudo-CLs, which is implemented in the Nemaster code. We use Nemaster to measure 10 auto and cross-correlation power spectra for the 4 redshift bins that Tianqing just described. And in our cosmological analysis, we only consider scales between an angular multiple of 300 and 1800. In addition to our power spectrum measurements, we also need a measurement of the covariance of the power spectrum. So we measure the covariance using a suite of 1400 mock catalogs, which use actual HSC year 3 galaxy positions, and apply a lensing signal based on the simulations from Takahashi 2017. So with that, we can measure the power spectra from these mock catalogs and get a set of 1400 power spectra that we can then use to measure the covariance matrix. And you can see the correlation matrix for the Fourier space analysis on the right here, and you can see that it's very close to diagonal. This is one of the advantages of working in Fourier space. The covariance matrix doesn't have large off-diagonal components, which makes it much easier to work with and invert. So with that, we can take a look at what our power spectra and covariance actually look like. This plot shows the autocorrelation power spectra of the 4 redshift bins on the diagonal and the cross correlations on the off-diagonal. We're able to get a very high significance measurement of our power spectra with a signal to noise of 26.4 for our fiducial scale cuts. I've also included the best fit model on these plots in orange, and I'll talk a little bit more about how we get this best fit model in a minute, but you can see that it provides a very good fit to our data. So it's reassuring to see that we have this high significance measurement, and it's also reassuring to see that we don't have a detection of significant B modes within our fiducial scale cuts. So B modes correspond to the curl part of the shear field, and because lensing is caused by a scalar gravitational potential, you would expect it to be curl-free. So if we had detected B mode power spectra, this would be a sign that systematics, particularly PSF systematics, are contaminating our power spectrum measurement. However, within our fiducial scale cuts, the B mode power spectra are completely consistent with 0. So this indicates that we have a set of power spectra that is great for getting cosmology out of. So in order to actually get cosmological constraints, we need to compute the likelihood of our observed power spectrum given some set of parameters. And we do that by comparing our observed power spectra to the theory prediction for those power spectra at that set of parameters. We then evaluate this likelihood throughout our parameter space using the polychord nested sampling algorithm, which is implemented in Cosmosis. So our power spectrum model is based on 23 parameters. This includes 5 cosmological parameters, 6 astrophysical parameters, which account for baryonic feedback and intrinsic alignments, and 12 parameters that account for observational systematics, particularly redshift distribution uncertainties, which Tianqing just told you about. And so with that, we can take a look at our actual constraint on S8. So we get a 4% precision constraint on S8 with a value of 0.776, where we're reporting the 1D marginalized mode. We have a 68% confidence interval of plus minus 0.033. And as I mentioned earlier, our best fit model provides a very good fit to the data with a p-value of 0.42. We've also conducted a number of tests before unblinding to show that our constraints are robust to the different modeling and analysis choices that we've made. In particular, we look at different choices that we've made throughout the analysis to ensure that changing any one choice doesn't significantly affect our constraint on S8. So we look at the effect of using a different sampler, sampling different parameters, using different astrophysical models, as well as different systematics models. And then finally, we look at the effect of allowing neutrino mass to vary because we kept it fixed in our fiducial analysis. As you can see, the constraints on S8 from these different tests all agree with our fiducial constraint well within 1 sigma. The exception to this is the case where we use an informative prior on the shifts in the 3rd and 4th redshift bin. In this case, we see a 1 sigma shift in S8 to a higher value. However, as Tianqing discussed, we get significant detections of large shifts in these bins, which would be inconsistent with this informative prior. And so this informative prior test appears to be revealing a real issue with our high redshift bins that is fixed by the uninformative prior that we use in our fiducial analysis. In addition to testing these modeling and analysis choices, we also do a number of internal consistency tests on our data, where we look at the S8 constraints from individual fields on the sky, using different redshift estimation codes, removing each redshift bin from the analysis in turn, and using different sets of scale cuts. And once again, you can see that the constraints from each of these tests agree with the fiducial constraint within 1 sigma. And so with this robust constraint on S8, we can look at how it compares to the constraints from other recent cosmological experiments. So our constraint on S8 is shown on the rightmost panel here, and you can see that it agrees well with the constraints from other recent cosmic shear experiments, particularly those from the Dark Energy Survey year 3 and KIDS 1000. However, our constraint is in about 2 sigma tension with the constraint from Planck 2018. So with that, hopefully I've convinced you that we have a strong, robust constraint on S8 that uses conservative modeling choices and agrees well with the constraints from other recent cosmic shear experiments while being in 2 sigma tension with Planck. I'll now hand it over to Shengcheng to tell you about the cosmic shear analysis using 2-point correlation functions.
Thanks, Ruhi. So, in addition to the Fourier space analysis introduced by Ruhi, we also constrain cosmology with real space 2-point convolution functions. Which is complementary to the Fourier space analysis, since we analyze it on different scales. The modally choices are coordinated between the real space and Fourier space analysis. So, as shown by the figure in the right, in the left, we measure the auto and cross correlation between the 4 redshift bins. In total, we have 10 correlations, and each 2-point correlation has 2 components. One is psi plus, and the other is psi minus. Psi plus is the tangential correlation between the galaxy shape, and the psi minus is the correlation at 55 degrees. So. And the black line in the left figure shows the best fit model of the 2-point correlation function, and the figure on the right shows the covariance matrix estimated from 1,400 MOGs from the ray tracing simulations, and the total signal to noise ratio of the measurement is 26.6. Before we run the constraint on the real data, we did many tests on the noiseless MOG data vector. our task covers to quantify the systematics bias from the like the projecting the high dimensional posterior to the 1D posterior, and also the modeling systematics from the linear power spectrum and the nonlinear power spectrum, and also the modeling uncertainty from the bionic feedback. So our conclusion is that all of this modeling systematics is within 0.3 sigma of our constraint. And the figure on the right, it shows our fiducial constraint, and we get a 4% precision constraint on S8 with a value of 0.769, and this is the 1D modularized mode. As in the Fourier space analysis, our best fit model provides a very good fit to the data with a p-value of 0.22. And in this slide, in the left panel, we show the comparison between the real space and Fourier space analysis. So even though we have really different weight on the scales, but our constraint is very consistent with each other. And the figure on the right, it shows the comparison with other weak lensing surveys and the Planck constraint. So our constraint is consistent with other weak lensing surveys, but in like about 2 sigma tension with Planck. Yeah, this is the end of me, and now I'll hand on to Sunil to introduce the 3cos 2-point analysis.
Thank you, Sanchon. Hi, everyone. I'm Sunil Sugiyama, and I was a graduate student, and I now just became a postdoctoral researcher at Cabri IPMU. In my presentation, I show the cosmological joint analysis, so-called 3x2 PT analysis, using Subaru HSC ER3 and SDSS data. Here is the survey footprint of the HSC ER3 in blue and SDSS DR11 in orange. The HSC survey is designed to overlap with major external surveys, and the SDSS is one of them. We performed the joint analysis by cross-correlating the spectroscopic galaxies from SDSS catalog as lens galaxies and shape galaxies from HSC ER3 catalog as source galaxy of weak lensing. And we divided the SDSS galaxy into 3 redshift bins, as shown in the bottom panel. To make cross-correlation of weak lensing, between HSC and SDSS galaxy, we selected an HSC galaxy so that the source galaxy are well beyond the lens galaxies. Thus, the source sample definition used in this analysis is different from that of the tomographic cosmic shear analysis, led by Ruby and Shanchan. The 3x2 PT analysis is a joint analysis of the 3 different kinds of 2-point correlation functions, the idea of which is shown on the left-hand side. The first probe is the autocorrelation function of foreground lens galaxy from SDSS, which is measured in the full SDSS footprint, and we call this galaxy clustering WP. And the second probe is the cross-correlation of shape of HSC galaxy and the position of SDSS lens galaxy, which we call galaxy-galaxy ranging delta sigma. And the last probe is the autocorrelation of the shapes of the HSC galaxies, which we call cosmic shear. The measurement result is shown in the middle. From top to bottom, the measurement of galaxy-galaxy clustering and galaxy-galaxy ranging and cosmic shear are shown. As done in the tomographic cosmic shear analysis, we performed the null test for cosmic shear and also galaxy-galaxy ranging and galaxy clustering as well. Based on the null test, we determined the data vector used for cosmology analysis, which is shown in the shaded region. One interesting point of the 3x2 PT analysis is that the 3x2 PT analysis can break the degeneracy of the model parameters. On the right-hand side, I show how these correlation functions depend on the cosmological parameter and galaxy bias parameter. We can see that due to the presence of the galaxy bias parameter, B, the cosmological parameter cannot be constrained if we do not combine them. Once we combine these probes in a joint analysis of 3x2 PT, we can break the parameter degeneracy like this. This is a demonstration of how parameter degeneracy is broken with MOF. And this is the unique point of the 3x2 PT analysis, the parameter degeneracy breaking. One of the largest challenges in the 3x2 PT analysis is again the photometric redshift uncertainty as explained by Tianqing. Especially for 3x2 PT analysis, we selected the HHC source galaxies at very high redshift. So there is a potential error in the photometric redshift estimate due to the lack of calibrator at such a high redshift. To tackle this problem, we introduced a nuisance parameter for the error in the mean source redshift, delta Z. For this parameter, previous work conventionally employed the very tight informative prior, which is the Gaussian prior with an error of about 1% level. But in our HHC year 3x2 PT analysis, we decided to use uninformative prior for this photo Z parameter. This is a very conservative choice, and we can cover any large potential error in the mean source redshift. We also emphasize that even if we use this uninformative prior, we can self-calibrate this photo Z parameter from the information of galaxy-galaxy ranging in 3 SDSS range samples. This self-calibration of photo Z is based on the spec Z SDSS ranges and thus independent from the tomographic cosmic shear analysis, which use low redshift photometric HHC galaxies as calibrator. To test our model and analysis choices, we performed the validation test. We tested our analysis method by analyzing the mock data and checking whether input cosmological parameter can be recovered or not. We simulated various kinds of systematic uncertainty as surrounded red rectangle, galaxy halo connection, baryonic feedback, and the observational effects like photometric redshift and PSF leakage. Overall, we found that our analysis method can recover the input cosmological parameter within 0.5 sigma level. Especially in this role, we found that even if the data includes huge photometric error as large as -0.2 level, we can recover the input cosmological parameter thanks to the conservative choice of our prior on photo Z parameter and the self-calibration power by spec Z SDSS ranges. After passing these model validation and various internal consistency tests in the blind analysis, we obtained the cosmological parameter constraint from the 3x2 PT analysis. The result is this. We performed two different cosmology analyses on the same data vector. One is the large scale analysis shown in pink, where we use the simple minimal bias model for galaxy bias modeling at large scale. The other analysis is the small scale analysis shown in blue, where we use emulator-based halo model. From this small scale analysis, we obtain a 5% cosmological parameter constraint. We found that the results from large scale and small scale analysis are statistically very consistent with each other. And this indicates that there is no significant or unknown galaxy bias uncertainty. The photometric redshift error we obtained is not so significant as that from tomographic cosmic shear analysis, but we found that the significance increases to 1.6 sigma when we use BAO prior on omega matter. The last thing to note is that the small scale analysis is most sensitive to the SH prime parameter, which is defined in the bottom line. And the small scale analysis gives 4% constraint on this parameter. Finally, we compared our cosmological parameter constraint to the external survey's result. We found our result is consistent with dark energy survey and kilodegree survey. And when we combine our result to the Planck 2018 result, we found 2.5 sigma level tension, which indicate SH tension. Before closing this presentation, I shortly describe the internal consistency test of the HHC result. The real space and Fourier space tomographic cosmic shear analysis and small scale 3x2 PT analysis. In order to take into account the cross covariance of these different analyses, we performed the simulated analysis on 2000 noisy mock data after unblinding. The left panel shows the difference of the estimates from 3 different analyses. And we can see that our result from real data shown in red agree with noisy mock analysis result. From this result, we concluded we concluded that our HAC year 3 results are statistically fairly consistent with each other. I now pass the spotlight to Ruth. He summarized our results.
Thank you, Sudha, for summarizing the 3x2 point analysis, as well as the consistency between the different cosmological probes that we heard about today. And I thank all the speakers for presenting these interesting results from HSC. So as a summary, we have successfully carried out multiple blind cosmological analyses. And the results that you saw today, they were obtained as unblinded in the last few weeks. In this figure on the left, what you can see are our constraints once again in the omega matter S8 plane. So using data from HSC as well as SDSS BOSS, we obtain consistent cosmological constraints. These constraints come from our cosmic shear analyses, which were carried out independently in real and as well as Fourier space. And then the independent 3x2 point analysis, which combine the cosmic shear information with galaxy-galaxy clustering as well as galaxy-galaxy lensing, both on linear as well as quasi-linear scales. We should note that we have been very, very conservative in the choice of our priors, especially on the systematic uncertainty of the redshift distributions. We are currently working on tests of the shear ratio with spectroscopic lens samples. This is in order to help mitigate the uncertainty, but in a data-driven manner. So in the flat lambda CDM framework, we are able to constrain the parameter S8 with an accuracy of about 4% with our cosmic shear analysis. And then if you look at the combination of S8 and omega matter, then we can constrain this combination with a similar accuracy with our 3x2 point analysis. To summarize, in the lambda CDM framework, we find a difference in the S8 omega matter plane of about 2 to 2.5 sigma, where the amplitudes are lower than that expected from the CMB experiment Planck. So in the next slide, I'm going to show the slide that was used by Hironao as well, which shows the results from the 2021 SNOMAS summer study, shows the current status of the various measurements of the parameter S8 in the literature. Again, early universe in blue at the top and later universe in the bottom. The different colors just show the different kinds of measurements. So our measurements from today are at the locations that you can now see here on the plot. So the question is, are we reaching the limits of the standard cosmological model? Although the difference between our HSC measurements and that of Planck is not really at the 5 sigma gold standard, it is indeed encouraging that all weak lensing surveys seem to be pointing in the same direction. But given the significance, this question definitely needs some more work. But the HSC survey is now complete, and it has surveyed about 1,087 square degrees of the sky in the G, R, I, Z, and Y bands. So this data is currently being processed at the NAOJ using the latest Rubin science pipelines. The HSC data is thus serving as a great test bed for the data host that will arrive with Rubin LSST. But before that data arrives, of course, we need to analyze the data from this final release of HSC. And indeed, it will be quite challenging. We'll have to address various issues as well as climb various systematic walls, in particular, those related to things like the blending of galaxies, given the depth of the survey, the various PSF systematics, as you heard about today, as well as the source redshift uncertainties, among others. Finally, I once again would like to share this slide that shows the key weak lensing working group publications relevant to the results that we presented today. And the various products of the HSC weak lensing group, like the shape catalog related to these analyses, they will be made publicly available once the manuscripts are accepted. Also, the recording of this webinar will be made shortly available at the URL, which is mentioned below here, as well as based on the QR code. So now we are happy to take any questions. Please send them to the webinar Q&A. And then I thank you for your attention. So with that, I will turn over to Rachel Bandelbaum, who will moderate the question and answer session for us. Thank you.
Thank you, Surhood, and all of our speakers. And hello, everyone. I'm Rachel Mandelbaum, and I'll be moderating the Q&A session today. Our panel that will be answering questions includes all of our excellent speakers, plus me and Masahiro Takada, and Marcus Rao, who led a paper we've highlighted today on N of Z inference, and who we are fortunate can now join us after some schedule changes. I'd like to thank the audience for all of the great questions you've already put in the Q&A, some of which are answered in writing and others that have been highlighted to answer live. Some of the questions will be asked as is, but to cover as much material as possible, I may reorder, modify, or combine some of them. And you can certainly keep adding your questions after this point or upvoting the existing questions, and we'll do the best we can to get to them. Many of our panelists can stay on the webinar longer than 1 hour, so we may continue up to 15 minutes beyond that point if questions remain, with thanks especially to my colleagues in Japan for staying on the webinar so late. Finally, please check out the website with the papers, and if you have questions after the webinar, reach out to the lead authors. And if you have put questions with your name attached in the Q&A, we may also reach out after the webinar if we have additional follow-up. So with that, I'm going to segue into the first question. This first question is going to be for Sunao. So Christopher Duncan is asking if magnification is modeled and or marginalized over in the 3x2 point analysis, because that can induce large delta Z shifts, particularly at high redshift. Sunao?
Yep. Thanks for your question. Yes. Answer is yes. Yeah, due to the presence of the shared large-scale structure between lens galaxy and source galaxy, there's a magnification, so-called magnification bias effect on the galaxy clustering. So we take into account the galaxy magnification bias effect on the galaxy ranging signal, and we also take into account the photo Z shift in that galaxy ranging model.
Thank you very much, Sunao. The next question is for Ruhi, and it's about slide 34. So Surhood, if you could please go to slide 34, that would be great. So the question is that removing redshift bin seems to make the error bar smaller than the fiducial result. Do I see that right?
Yeah, that's a great question. We didn't have time to cover the details in this short talk, but what we realized is that when doing this test, if we use an uninformative prior on our third and fourth redshift bin, and then remove bin 1 or 2, we would lose all the constraining power of our analysis. And so rather than using that uninformative prior here, we used the posterior on the third and fourth redshift bin shifts from the fiducial analysis as the priors for those shifts. And that's why it's not an incorrect prior in the sense of a Gaussian centered on 0. It's the priors coming from the fiducial analysis, but it is more informative than the one we use in our fiducial analysis. And that's why you see smaller error bars here.
Thank you very much for that explanation. So the next question, I'd like to direct to 2 different people. The first one is to Sheng Chang for cosmic shear, and then Sunao to comment on the 3x2 point analysis. So Benjamin Yoakimi says, congratulations on these highly anticipated results. Could you say a few words about how you model intrinsic alignments and baryonic feedback, and what constraints you obtain on the free parameters of those models? And I believe Sheng Chang may have a backup slide to point Surhood.
Oh, yes, thanks for the question. Surhood, can you go to slide 16.8? So 16.8. Yeah, this so we are using the TAT model as our fiducial intrinsic alignment model, and this plot, it shows the the difference between our fiducial and the NLA and without modeling the intrinsic alignment at all. So basically we're showing the first like intrinsic alignment amplitude, which is A1. I think this is like 1 sigma, like it's not a significant detection of the intrinsic alignment. And if we go to the next slide, this is our modeling of the bionic feedback. So we are using the 2016 version of the HM code. And so that code, there's a free parameter that's called A baron. The invariant equals to 3.13 is corresponding to the one without the bionic feedback. So we have a strong detection of this bionic feedback since the result like the 3.13 is like outside of the 1 sigma confidence region of the posterior. It's like.
Thank you, Sheng-Chang. And I wanted to ask if Sunao would like to comment on the baryonic physics and intrinsic alignments modeling for the 3x2 analyses.
Yeah, we use different approaches from cosmic shear tomography analysis. In the 3x2 PT analysis, the most largest signal to noise ratio is coming from the galaxy clustering and galaxy ranging. So we didn't explicitly include the baryonic feedback effect, but rather validate our model analyzing the mock data, including baryonic physics. Can you go to the slide 44? Yeah, in the from the HM code section, we simulated mock data which is affected by baryonic feedback effect, and we analyzing this noise mock data without including baryonic effect. And due to because the signal to noise ratio, as I explained before, is coming from the galaxy clustering and galaxy ranging, we did not find significant shift in the cosmological parameter, especially S8, even if the baryonic effect is present in the data vector. And for intrinsic alignment, we also included we included that effect in the model using nonlinear alignment model, but we didn't find any significant detection of the intrinsic alignments from 3x2 PT analysis. Thanks.
Thank you, Sunao, for answering that question for 3x2 point. So we have a few different categories of questions next. The first one I wanted to address is we got 3 questions that were about either the orientation or the size of the 3x2 point contours compared to the cosmic shear contours. So Sarhad, I was wondering if you could please go to a slide that shows those contours together. And yeah, so there were questions from Bhuvnesh Jain, John Franklin Crenshaw, and one more person. I'm sorry, I'm not finding it at the moment. Could you please comment on the orientation of the 3x2 point contours, which look different from the cosmic shear results here on this slide, and also the kids constraints on another slide. Yeah, that's the first part of this question. Just can you comment on the orientation, please, Sunao?
Yeah, thanks for your comment and question. So in this blue contour, we use a small scale analysis, small scale information of the galaxy ranging and galaxy clustering down to roughly 2 megaparsec level. And in that level, we also model these probes with a halo-based model. In that, we have additional cosmological dependence on the halo mass function. And small scale information also has an additional scale dependency compared to the large scale. So this gives slightly different sensitivity to the S8 parameter. So this is the reason why we get different degeneracy direction between S8 and the.
Thank you. And then a related question is, have you checked if you find tighter 3x2-point S8 constraints if you use a different tilt in the S8 definition, not the 0.5 power, but something else?
Yeah. Can you go to the? Yeah. This slide basically answered your question. So if I define a different S8, which is defined sigma 8 times omega beta 2.22, so this, small scale analysis basically gives tightest constraint on this parameter. So
Thank
this,
you.
yeah.
Oh,
4%.
sorry.
Yes, sorry.
And this is, sorry to put you on the spot yet again, but a very related question. Just, checking, is it true that the error bar on S8 is larger for 3x2-point than for cosmic shear? When you expect the opposite, how can you explain that? Oh, so now you are muted.
Oh, sorry. Sorry. Yeah, in our analysis, we adopted very conservative choice of the photometric redshift prior, which is completely flat prior on the photometric redshift. For this, the calibration of photometric redshift is basically coming from the galaxy ranging, and there is also calibration power from cosmic shear analysis. So when we combine this galaxy ranging and cosmic shear in 3x2-pt analysis, we have enough constraining power on the photometric redshift residual error. But on the other hand, if we analyzing 2x2-pt alone or cosmic shear analysis alone, so we can, in that case, we cannot unfortunately get sufficient power to constrain the photometric redshift error. So yeah, in order to get meaningful constraining power or perform a stress test or internal consistency test, we adopted the prior on the photometric redshift error, which is taken from the baseline 3x2-pt analysis. So this is the reason why we get a smaller error bar in the 2x2-pt alone and cosmic shear alone analysis.
So now it may also be worth reminding listeners that the cosmic shear in the 3x2-point only includes a high redshift source sample. It doesn't include all of the tomographic samples used in the cosmic shear papers. And so in this particular analysis, you shouldn't think of cosmic shear as being a subset of the 3x2. I noticed a few questions in the Q&A about that. Okay, thank you, Sue. Now we'll give you a little bit of a break and go to some questions about the redshift calibration and the redshift prior. So the first one I would like to pose as a question to Marcus, and I wanted to ask Sirhood if he could please go to slide 23, which I think will be helpful background for this. So the first question was from Angus Wright, who asked, did I understand correctly that the posteriors of the delta Z parameters in the two highest redshift bins prefer shifts of 0.1 and 0.2? I will personally just interject that the magnitude of the shifts depend on which analysis. Real and Fourier space have slightly different ones, but broadly there are significant size shifts in those bins. So the question based on that is, how confident are the authors about the accuracy of the redshift calibration process if it is able to hide shifts of that magnitude? And I think the redshift coverage of Chimera LRG shown on here with a line is relevant to that. And I'll hand it off to Marcus to answer.
Yes, indeed. So one aspect that one has to take into account that we don't have Chimera LRG coverage, redshift coverage beyond 1.2. And our confidence in our redshift calibration is informed by the consistency between our photosy results that are based on photometry, which is shown here as a gray contour, and our results from the cross correlation. So when we go beyond 1.2, we of course lose confidence because we don't have clustering redshifts to compare against. Another aspect that is a motivation for the very conservative choice of prior and a higher tomographic redshift bins is, of course, that redshift calibration in our case is also supported by spectroscopic data that gets cannot be expected to be complete specifically for these high redshift tomographic samples. So I think that's a good motivation for choosing conservative priors, and it's really not to hide certain aspects, but to parameterize our conservative assessment of our photosy calibration. I hope that answers the question.
Yeah, thank you, Marcus. And I wanted to ask a follow-up question also from Angus for Shengchang. Does the conservative prior on the redshift distribution shifts in the third and fourth bin assume that the redshift uncertainties are uncorrelated?
Thanks for the question. Yes, that assumes they are uncorrelated. So we don't model any correlation but we have a really wide prior. I think the prior is ranging from -1 to 1. So on the last two redshift bin, but that doesn't include any consideration of the correlation. But I mean from the posterior, so we can have the constraint on the posterior of the shifting arrow, but the posterior they are quite correlated, but the prior they are not correlated. Yeah, that's the information from.
Thank you, Shengchang. So the next question is for Sunao. Slide 41, please. And apologies to if I misunderstood the question, but the question was, do you address the cosmic covariance between your survey and the other surveys due to footprint overlap? And I thought it was asked when we were around this slide, so I wondered if it was about HSC and SDSS BOSS overlap. Apologies again if I misunderstood. But so now, can you comment on that, whether we include covariance for that?
Yeah. Assuming we understand the question correctly, yes. The answer is yes. When we compute the covariance matrix, we use full sky simulation, and in that simulation we simulated shape weak ranging shape distortion in the on the galaxy shapes observed in AGC galaxy, and we also populated SDSS like lens galaxy in the same simulation box, so full sky simulation, so we can properly take into account the cross covariance and the overlap of these SDSS and HSC footprints.
Thank you, Sunao. The next question is the next question is for Hiranao. So this question is from Anthony Lewis. So it's about the type prior on omega CH squared for the 3x2 point. And whether that's cutting off the posteriors in a way that correlates with the bias. So what was the reason for this prior choice? And in the comparison of 3x2 point and cosmic shear contours, how much of the difference is due to the different priors chosen for omega c h squared.
Yes, can you hear me?
Yeah, we hear you.
Okay, great. Yeah, this is a good question. So I'm assuming you're asking about the 3x2-point analysis because you showed this number. But right, so this is limited by the fact that well, supported emulator range is limited, as written in the paper. And so if you look into the paper, so we tested actually the final 3x2-point constraint posterior of the final 3x2-point constraint. I mean, it's almost within emulator support range. 95% CI confidence interval is within emulator support range. And yeah, so I think that it's safe to assume that this prior, well, also this is a flat prior, of course. And also for the question, well, in a comparison part 3x2-point lensing context, how much a difference in shape location is due to other choices for the cosmology prior. I think that this is a question about the left panel of the figure 6. And where I would say like cosmic shear and the 2x2-point are not our fiduciary analysis, but still majority of the posterior is already searched. So it should be, I mean, okay, just for the demonstration. But if you wanna seriously look into the constraining power by these two probes, of course, we need emulator with a wider omega c range. But yeah, this can be a future work once such emulator is available. Yeah, that's it.
Thank you, Hirano. Okay. So the next question I would like to direct to begin with to Surhood, but then he could hand off to any analysis leads he thinks appropriate. Surhood, can you go to slide 48, please? Okay, so the question is, are the constraints in the sigma 8 omega matter plane consistent between the 3x2-point and the cosmic shear 2-point function analyses, and in particular, focusing on whether there might be a shift in the omega matter direction with the 3x2-point being higher. I did want to just say as a preamble to this that we're working on a detailed, consistency analysis to hopefully result in a separate paper. But I wanted to also let Surhood and any analysis leads comment on this as well.
Yeah, sure. Thanks, Rachel, for directing this question to me. So we did run consistency test between these different analyses, in particular for the results of S8. So as Sunao showed, for example, we did check that the results of S8, when comparing the real space to the 3x2-point and then the Fourier space to the 3x2-point, we do get values which are consistent with what we observe from noisy mocks. There's a reason why we did not compare omega matter in particular. And that was because if we just look at the cosmic shear analysis, then there are sometimes some indications that the omega matter results that we get may be a little bit biased. And I think Ruhi can explain a little bit about this in case she has a backup slide. And so that was one of the main reasons that we focused mainly on the S8 parameter in these internal consistency tests. But this particular paper is not there on the archive today, but you will see it soon as well. So Ruhi, do you want to explain the issues related to omega matter?
Sure. Could you maybe start by going to slide 66? So one of the reasons why we're not focusing on reporting a constraint for omega matter in the cosmic shear analyses, particularly the Fourier space cosmic shear analysis, is that we found that for our fiducial range of scale cuts, we're not really able to break the degeneracy between sigma 8 and omega matter. So this plot shows on the left the ratio of CLs, angular power spectra, for two different points along the sigma 8 omega matter degeneracy. These 2 points have the same value of S8, but one is a very low omega matter, high sigma 8. The other is a very high omega matter, low sigma 8. And you can see that for our fiducial range of scale cuts, which are marked in the shaded region, the ratio of the CLs is nearly 1. And so we kind of knew from the beginning that we don't really have constraining power along the degeneracy direction. Moreover, when we did model validation tests, so if you go to slide 63, where we simulated contaminated data vectors and analyzed them with our fiducial model to ensure that model misspecification wasn't biasing our results. We, if you look, the plot on the left shows the bias recovered in the omega matter S8 plane from these model selection tests. And we found that generally the bias is larger in the omega matter direction and not so large for S8. And sort of as a result of a number of these tests, we realized that we're not really able to confidently constrain omega matter. And so we're really focusing on our S8 results here.
Thank you very much to Sarhud and Ruhi for that explanation. I wanted to ask a somewhat related question to Sunao. For 3x2 point, when you did the analysis, did you test the consistency between 2x2 point and cosmic shear as part of that project?
Yeah, thanks for your question. Yeah, that's a really nice question. But unfortunately, I have just nice figure for now. But we actually performed this kind of analysis. So 2x2 PT and cosmic shear analysis in with single source beam has share the same HCC source sample. So there is a potential correlation between 2x2 PT and cosmic shear analysis. So to take into account this possible cross covariance between 2x2 PT and cosmic shear with single source beam, we performed hundreds noisy mock data analysis, and we tested the agreement between the 2x2 PT cosmology constraint and the cosmic shear constraint, and we found that the result from 2x2 PT and cosmic shear are fairly consistent with each other.
Okay, thank you, Sunao. I'm gonna take one more question and then I think we should call it a day because it's been a long morning or evening for our speakers. So I'm going to take a question about the galaxy-galaxy lensing in the context of the 3x2 point. I'd like to direct this to Hira now. So the question is, how much does the galaxy-galaxy lensing contribute to the 3x2 point constraint? Because in KIDS 1000, they found that the cosmic shear and BOSS clustering dominate over the KIDS cross BOSS galaxy-galaxy lensing due to BOSS having so much larger sky coverage than the common area.
Yeah, yes. Okay. Good. Can you hear me?
Yes, we do.
Okay. So yeah, that is simply because we didn't include BAO or RSD. Well, as Sunao talked about, so we use WP, the projected cohesion function, rather than 3D clustering. So the joint analysis with 3D clustering can be done somewhere. We already have an emulator for that. So yeah, so let's please stay tuned.
Okay, well, thank you very much. I'd like to thank all of our panelists. for answering the Q&A. There are a few outstanding questions, but it's been a very long session. So I see the remaining questions do have names attached, and so we'll follow up individually with those who asked them. So thank you very much, everyone. And you'll be able to see the papers on the website and on archive tonight.